So my name is Tania Lombrozo. I'm a psychology professor here at Berkeley. And I hope to convince you in the next few minutes that learning isn't just about getting the right information. So here I think is a popular and intuitive view of how you might think learning works. And I call this the bucket model of learning. And the idea is that the world confronts you with all sorts of novel information and new data. The way that learning works is that somehow you copy or transfer this new information into the mind. You've learned something new in the sense that you have acquired new information. Now, while I think that very few psychologists would actually explicitly endorse this as an adequate model of how learning works, you find that models of learning overwhelmingly focus on how it is that we acquire new information and how it is that our beliefs are updated in light of new information. So the picture is something like this. You can imagine the learner at time 1 and at time 2, where a learning event has occurred, and the critical thing that's changed between those two moments is the acquisition of this new information. Now, part of the reason why thinking about learning in this way might be so intuitive is because most of the cases of learning that I think that we think about follow the model of learning from observations. So for example, these are cases where you might learn about somebody's personality by observing how they behave. You might learn about the relationship between two variables, x and y, by seeing their patterns of co-occurrence. Many, many instances of learning are cases of learning from observation, and the majority of cases that psychologists have studied when they study learning are cases that look like this. Another example that follows this model is a special kind of observation, which is when we learn from testimony, right? When we learn from other people who are typically more informed than us in these kinds of learning cases. But what I want to argue is that at least some of the time, really deep and interesting and profound cases of learning happen even in the absence of new data. So this is a phenomenon that I refer to as learning by thinking. The most celebrated cases of learning by thinking are thought experiments or Gedanken experiments in the history of science. So for the most part, science proceeds by going out and making observations and conducting experiments. But some of the time in the history of science, there have been really important episodes where we've made some kind of advance without the benefit of new data, right? An experiment in the mind, a thought experiment, has led to some really important advance. So there are many famous examples of this, from Einstein thinking about relativity. Another example I have up here is Schrödinger's cat. But there's many other famous examples as well. Galileo had a very influential thought experiment that overturned ideas about Aristotle and gravity. You also see this kind of thought experimentation in philosophy. So if you've ever taken a philosophy course or you've encountered philosophy, you've probably been invited to imagine all sorts of cases like runaway trolley cars and brains in vats and twin Earths and zombies and so on. And again, some of the time it seems like we get some genuinely new insight, some genuinely new learning or understanding as a result of engaging in this type of thinking from the comfort of our armchair without any new data from the external world. So one thing I hope to convince you of is that this isn't a phenomenon that's actually restricted to scientists and philosophers, that actually everyday life is full of cases of learning by thinking. So for example, if you're trying to imagine what the best floor plan is for a house, one thing you could actually do is the real experiment. You could build 5 different houses with 5 different floor plans and actually go into them and experience them. And you can see why this would be extremely impractical and inefficient. But we're actually able to, from the comfort of our armchair, perhaps in this case with the help of some paper and pencil, to be able to think through what different sorts of things would be like. So we don't have to do the actual experiment of creating these different structures. We can gain a lot of insight just by doing a kind of mental simulation. And this is true for other cases as well. So for example, if you're trying to decide whether you'd prefer a holiday scuba diving or skiing, the actual experiment would be to do both of these and compare them. And of course, we'd all love to do that if we can. But some of the time, you can actually get some pretty reliable information about what sorts of things might be like by engaging in a kind of mental simulation. So the case of learning by thinking that I've studied in my own work is a case that you've probably all experienced, which is learning by explaining. So I'm guessing that everyone here has had the experience, at least some of the time, of explaining something to somebody else or to yourself, perhaps in the course of writing a paper, or tutoring someone, or talking to a child or a colleague or a student. And in the course of explaining to somebody else, you come to understand something better, right? And this is learning by thinking because you're not being explained to. You're not the one who's getting new information. Something about the process of generating an explanation for yourself or for somebody else can sometimes lead to genuinely new learning or insights. This is a phenomenon known as the self-explanation effect that's been studied in the educational literature. And basically what you find in these cases is that when you prompt people to explain pedagogical materials, like examples of worked math problems or a passage of text about biology, students typically learn better and generalize more readily to novel contexts than when you compare those students to those who engage in some other kind of learning strategy, like reviewing the materials twice or just spending a matched amount of time studying. So we've taken an experimental approach in my lab to try to understand what's going on in these cases of learning by thinking, and in particular learning by explaining, such that you can end up with genuinely different learning as a result of the process in which you engage, even though you don't have new information. And the way that we've done this is by assigning people randomly to one of two conditions, where what we do is we prompt one group to explain while they engage in some kind of a learning task, and we prompt the others to engage in some sort of control task, like thinking aloud. The critical thing here is that all of our learners have the exact same learning goal. We tell them that they have to learn, for example, how to classify objects or how to learn a causal relationship, and I'll show you examples of this in a moment. They all are exposed to exactly the same information. And so if we look at our learners at time 2 here, and find that there's something different about what they've learned or that the inferences they're drawing, we know that it's not attributable to the information that we presented them within the task because that's been matched across our conditions. If we're finding differences in what people learn, it has to do something with the process that they've engaged in trying to reason through that material. So let me show you a concrete example of this phenomenon. This is one of the cases that we've studied in my lab. These were studies with a graduate student named Joseph Williams, where we brought people into the lab and we had them learn about these robots from an alien planet. So here are 8 examples of these robots, 4 glorps and 4 drents. And if you were a participant in this study, you would be asked to try to learn how to differentiate glorps and drents, because I'm later going to show you some new robots and you're going to have to tell me if they are glorps or drents. Now, we designed these so that there's lots of different things going on. There's colors, there's shapes, and so on. Our participants have more time to figure this out, but I'm just going to give away one of the important things going on here. So that we've designed these so that there's a relatively subtle rule that underlies the classification of glorps versus drents. So if you look at their feet, you might notice that they all have uniquely shaped feet, but all of the glorps have feet that are pointy at the very bottom, and all of the drents have feet that are flat along the very bottom. So what we were interested in was whether or not prompting people to try to explain to themselves why each of these might have the category membership it does would make them more likely to go beyond all of these superficial chaos of different kinds of features they might be focusing on to try to find some kind of a broad underlying regularity that might not be obvious, but that allows you to classify all of these into these 2 groups. And that's what we found, but let me show you how it worked. So participants were introduced to these 8 examples. They then had opportunity to study them. And what we did is that they always had all 8 for reference, but we then showed them on screen one of these robots at a time. And half of our participants were prompted to explain why they thought that particular one was a glorp or a drent. So you might see this one and you'd have to explain, why do you think this one might be a glorp? And they would provide a response without any feedback on the content or the accuracy of their explanation. And what we did across conditions is we varied what participants did in the control case. So we've done experiments where we compared people who were prompted to explain these robots to people who were prompted to describe them, to think aloud as they studied them, or just to engage in free study. And then we'd ask them, what did you learn about the differences between glorps and drents? And we can see, based on that measure and others, whether or not they discovered this relatively subtle rule about the shape of the feet and what else they might have learned about these items. And here what I'm going to show you is the proportion of our participants who discovered this relatively subtle rule about the feet across these experiments where we compare explaining to either describing, thinking aloud, or free study. And what you can see across these 3 studies is this fairly consistent pattern where just having prompted people to explain made them 2 or 3 times more likely to discover this subtle underlying pattern than participants in the control condition. Even though everyone had the same goal of learning to classify glorps and drents, everyone had the same information in the sense that they were all shown the same 8 examples. We've shown in other studies that this works for kids too. So these are studies with a graduate student named Karen Walker, also co-advised with Alison Gopnik, who you just heard from. And we used this device called a Blicket detector. We showed them there was this exciting toy. When some things go on the machine, it plays music and it lights up. When other objects go on the machine, nothing happens. Overall, they saw these 8 training examples, which were also available for them like this, so they didn't have to remember exactly what had happened, but they saw that these 4 had made the machine go. Those 4 over there had not made the machine go. The critical manipulation here was this. For half the kids, every time one of these objects went onto the machine, they were asked, why did this one make my machine play music? Or why didn't this one make my machine play music? The children provided an explanation. I should have said these are 5-year-olds. I don't think I gave you the age, so these 5-year-olds provided an explanation. The experimenter didn't give them any feedback about whether or not it was right or wrong. In a control condition, we wanted to have kids be equally engaged, draw equal attention to the relationship between the blocks and the detector, but not have them actually engage in explanation. So here they were asked, what happened to my machine when I put this block on it? Did it make it play music? And they would just say yes or no. The critical trials look like this. We showed them 2 blocks that were partially obscured. So you could see that one of them had green on top, but you couldn't see what was on the front. You could see that another one had red on the front, but you couldn't see what was on the top. And we asked them, which of these 2 do you think is going to make my machine go? So what we're really testing here is what it is that they were able to learn about the statistical relationships between these features and making the machine go in order to be able to draw this novel inference. Are they able to do that using the most reliable cues? Are they able to identify the fact that green is probably a better basis for predicting that the machine is going to go than red is here? And what we found is that the 5-year-olds in the control condition were at chance. They actually had no preference between these blocks. But the kids who'd been prompted to explain had a reliable preference for the block that had green on top, that had this feature that had been more strongly statistically associated with the outcome that they were trying to predict. So it looks like explaining in this case improved even young children's ability to use these kinds of patterns and data to guide their subsequent judgments. In other research I'm not going to have a chance to tell you about, we found that prompts to explain encourage learners to find broad and simple patterns that underlie what they're trying to explain, for better and for worse. So this is not always a good thing, right? Some of the time, there is no broad and simple pattern that underlies what you're trying to explain. And in those cases, trying to explain can actually mislead you. We found that explaining encourages learners to understand what they're trying to explain in the context of what they already know. So it involves a kind of integration with prior beliefs. And we found that explaining encourages learners to go beyond the obvious, focusing less on salient or superficial characteristics in these kinds of tasks features, for example, like the color of the robots in the first study, and more on important but unobservable properties like causal properties, category membership, and unobservable internal parts. So if we return to this kind of schematic here, one way to think about this is that our learners all have the same information, but they're processing that information very differently, whether they're explaining or engaging in some kind of other process. And in particular, when they're explaining, they're looking for a good explanation. And that's going to drive them to go beyond superficial obvious properties, to try to find some simple underlying broad regularity that accounts for what they're trying to explain. And what we would expect is that other kinds of processes are going to bring distinct sets of constraints in terms of the way that they influence the way that information processing occurs. And critically, this occurs even though everyone has the same information, right? And that's what makes these kinds of cases what I want to call learning by thinking. So let me end with a global lesson that I hope to draw here. The point isn't to argue that data doesn't play an extremely important role in learning. Clearly it does. Data is really, really critical. But I think what's useful about highlighting these cases of learning from thinking, highlighting these cases where learning seems to occur even in the absence of novel data, is that it encourages us to look at the other part of the process, which is not just the novel information, but how we process it, right? And I think that's what we really want our theories of learning to be focusing on, to tell us more about how it is that we represent and process information, because that's what's going to be really crucial to the way that learning works. And for these reasons, I think it's really important that we kick the bucket model of learning. So thank you very much to my funders, to my lab and collaborators, and of course to all of you for your attention.